You know those visual puzzles that seem totally impossible, but then you find out the solution was just hiding in plain sight the whole time? Well, that's kind of what we're doing today, but our puzzle comes from the world of geometry, specifically the super tricky concept of area. And it turns out when it comes to shapes, what you see is definitely not always what you get. All right, let's just dive right in. Take a look at these two shapes. We've got a nice, normal rectangle and then a parallelogram that's kind of leaning over. Just go in with your gut. Which one do you think takes up more space? Which one has the bigger area? Lock in your answer. We'll come back to it. I bet most of you are leaning towards the rectangle, right? It just looks so solid. The parallelogram, on the other hand, seems all stretched out and flimsy, like it's spread too thin. It really feels like an open and shut case. But here's the thing about geometry. The most obvious answer is often just a clever illusion. To find the real truth, we need to gather some clues. Now, before we can actually solve this thing, we've got to learn the rules of the game. See, geometers have a very specific way of talking about situations like this. And once we get a handle on two simple but absolutely crucial rules, the whole picture is going to snap into focus. First up is this idea of the same base. And, it's pretty much exactly what it sounds like. Imagine two houses built right next to each other on the very same slab of concrete. In geometry, when different shapes are sitting on the exact same line segment, we say they have the same base. It's the foundation of everything we're about to do, literally. Okay, the second rule sounds a little fancier, but don't let the words fool you. The idea is just as simple. It basically just means that all the shapes have the exact same height. So their bottoms are on one line, and all their top points just touch another line that runs perfectly parallel to the bottom one. So think, same base, same height. That's the combo we're looking for.
And boom, this diagram shows these two rules in action perfectly. Just look at that parallelogram, the rectangle, and the triangle. They're all totally different shapes, right? But notice how they're all sharing a common floor on that bottom line, and their ceilings all just kiss that same parallel line up top. They're like neighbors, all living on the same street with the exact same sized front yards.
Okay, so we've got our two ground rules. Now we are ready for the first big reveal. This is the secret that's going to crack our whole puzzle wide open. It's a super powerful idea in geometry, and it's called Theorem 19. And here it is. This is the secret sauce. Now, it's a bit of a mouthful, I know, but the idea itself is just so simple and so powerful. If you have a bunch of parallelograms and they all follow our two rules, they're on the same base and they have the same height, it does not matter how stretched or skewed or tilted they look, their areas will be exactly, and I mean exactly this. I know. That sounds kind of impossible, doesn't it? How can that wacky, skewed shape take up the same amount of space as a perfect rectangle? Well, let's prove it. On this page, you can see two parallelograms, ABCD and ABEF. They share the same base, AB, and they're squished between the same parallel lines. Our mission is to prove without a shadow of a doubt that their areas are identical. Now, the solution here is hiding in a really clever spot. It's not in that big overlapping part in the middle. The whole key to this puzzle is in those two little triangles on the ends, triangle ADF on the left and triangle BCE on the right. If we can just prove that these two triangles are identical, the whole thing falls into place. And proving they're identical is actually really straightforward. First, we know that opposite sides of a parallelogram are always equal, so that means side AD has to be the same length as side BC. Then, because we're working with parallel lines, we also know that the corresponding angles are equal. So, since we've got matching angles and a matching side, boom! The rules of geometry say these two triangles are congruent. They're perfect clones of each other. So if they're perfect copies, think of it like this. Imagine we could take a pair of scissors and just snip off that little triangle from the left side. Then we just slide it over and stick it onto the right side. Since it's an exact copy, it slots in perfectly, and just like that, it transforms the first parallelogram into the second one. See? We haven't added or taken away any area at all. We've just rearranged the pieces. And here's the mathy way of showing it. The area of the first parallelogram is just the area of that left triangle plus that big shape in the middle. And the area of the second parallelogram is the area of the right triangle plus that same middle shape. Well, since we already proved the two triangles are equal, it's just like saying 5 plus 10 is equal to 5 plus 10. The result is just undeniable. The total areas have to be identical. So that's the big secret for parallelograms. But check this out. This discovery doesn't just stop there. This exact same logic leads to something really cool when we look at their smaller cousins, triangles. If you take any old parallelogram and just draw a line from one corner to the opposite corner, that's called a diagonal, you'll see it slices the whole shape into two triangles. And that diagonal isn't just some random line. It's a perfect cut. It creates two triangles that have the exact same area.
And this leads us right to our next big idea, Theorem 20. It's super logical. If a triangle shares the same base and the same height as a parallelogram, its area is always going to be exactly half the area of that parallelogram. It has to be, because as we just saw, the triangle is literally one half of the whole shape.
Okay, now let's connect all the dots. This is the big payoff. If all those different-looking parallelograms on the same base have equal areas, and any triangle on that same base is exactly half of any of those parallelograms, well then, it just has to be true that any two triangles that follow these rules must also be equal in area to each other. So we've cracked the code for parallelograms and for triangles. We have all the clues we need. It's time to put this new knowledge into practice and finally solve the puzzle we started with. All right, we are back where we started. The nice, neat rectangle versus that skewed parallelogram. You've seen all the evidence. You know the secret rules. So, what's the final verdict? Which shape has the bigger area?
And the answer is, drumroll please, it was a trick question. Their areas are exactly the same. Our eyes totally fooled us, but the math doesn't lie. You see, a rectangle is just a special kind of parallelogram, one that isn't leaning over. Since they're on the same base and between the same parallels, their areas have to be identical.
Okay. Let's put this new superpower to the test with a real example. So, we're told that the parallelogram on the left, AFEC, has an area of 140 square centimeters. The question is, what's the area of the parallelogram right next to it, BFED? We don't even need a calculator for this. We just need our theorem. Let's run the checklist. 1. Are they parallelograms? Yep. 2. Are they on the same base? Yes, they're both standing on FE. 3. Same height? You bet, they're between the same parallels. So we apply Theorem 19, which says their areas must be equal. The answer has to be 140 square centimeters. It's that easy. So, what's the really big takeaway from all this? It's that these two simple theorems we just walked through, they're like having geometric X-ray vision. They let you look right past the way a shape looks, which can be super misleading, and see the hidden truth of the area inside. It really makes you think, doesn't it? We started with a simple little visual puzzle and ended up proving that what our eyes tell us about something as basic as area can be completely and totally wrong. Which leaves us with a really fascinating question. If our own intuition can be so easily tricked by something like area, what other deep truths about our world are just hiding out there, in plain sight, waiting for us to discover them?